Right. So last week we did additive ciphers. So basically we took a letter, we converted into a number, its position in the alphabet basically. So A is 1, B is 2, and so on. Then we added something. So what I might do is share the screen with you. Just turn the cameras on. Okay. So what we did last time, we took the letter B, which was in position 2. We added 3. We got 5, and that converted into A, B, C, D, E. That converted into B. So plain text B got enciphered, be very careful, enciphered into B. And we use the same addition each time. So this is why we called it an additive cipher. Now, if you start thinking about things a little bit, you say to yourself, well, we can not only add in our arithmetic, we can do multiplication. And that's exactly what this is happening. Oh, remember, everything wraps around. So if we take y, and which is the 25th letter of the alphabet, X, Y, Z, yep. We add 3, we get 25, 26, 27, 28. But we have to reduce it mod 26. So that's actually 2. And the second letter of the alphabet is B. So Y gets turned into a B. So take the plain text number of the letter, add a certain shift. That gives you reduce mod 26 if you need to. That gives you the ciphertext number of, the number of the ciphertext letter. We do the same thing with multiplication. So instead of adding a fixed amount, we can multiply by a fixed amount. So, if our multiplier is 3, then put it this way. So if we do a multiplier of 3, A is 1, times 3 is 3, and what's the third letter of the alphabet? C. So A gets enciphered to C. What about B? B is the second letter. We multiply it by 3, we get 6. We don't have to reduce it because it is already reduced. What's the sixth letter of the alphabet? The F. So plaintext B gets ciphered, gets encrypted into ciphertext F. K, 3 times 11. So basically, K is the 11th letter of the alphabet. We multiply it by 3, that's 33, but we've got to take it mod 26. I should actually put congruences there. Okay, let's just subtract 26, that'll do. So subtract 26 gives us 7. What's the 7th letter of the alphabet? A, B, C, D, E, F. Should become G. So plaintext K gets encrypted into ciphertext G. Yes. Oh, I didn't do it correctly. Z is the 26th. 26 times 3 is 78. Reduce it down to 52, then to 26. So basically, I just subtract 26 each time until I get a number between 1 and 26. And what's the 26th letter of the alphabet? That's Z. Now, what's really interesting about this is that a little bit like additive ciphers, not every multiplier works. So with the additive ones, you can add 1 or 2 or 3 or 4 up to 25. If you added 26, you just get back to the same thing. So if your additive shift was 26, your plaintext character A would become ciphertext character A. There would be no change. If you added 27, that's just like adding 1, because 27 in the MAT1MIT system is the same as 1. So something a little bit the same is happening here. But not all multipliers do the right thing. So this is actually a much more interesting. It's not just that not all multipliers give you the same thing, like, you know, adding 26 is the same as doing nothing, or adding 27 is the same as adding 1. But there are some multipliers that simply don't work. So if you continued this 3 business, you'd end up with this. So 1 goes to 3, 2 goes to 6, 3 goes to 9, 4 goes to 12, 5 goes to 15. So the 5th letter of the alphabet, C, multiplied by 3 is 15. 15th letter would be O for our ciphertext. What happens if we do a multiplier of 2? This is really interesting. A is 1. 2 times 1 is 2. Okay, B is 2. 2 times 2 is 4. C is 3. 2 times 3 is 6. D is the 4th letter. 2 4s are 8. H is the 8th letter. You get down to here. L is the 12th. M is the 2, 3, 4, 5, 6. M is the 13th. 2 times 13 is 26. Well, that makes sense. Two times 13 is 26. The 26th letter is Z. So we haven't had to do any reduction. Now, the interesting thing happens here. What happens to 14? Okay, 2 times 14 is 28. So what's the 28th letter of the alphabet? Well, there isn't one, but 2 times 14 is 28, but we're reducing it mod 26. So what do we end up with? 28 minus 26 is 2. What's the second character of the alphabet? B. That means plaintext A and plaintext N both get encrypted to B, which is going to be a bit of a problem in this particular case. I mean, there are some times when it isn't a problem, but there are times when it is a problem. This is a time when it's a problem. It's also, you can see what's going to happen next. The 15th letter O, 2 times 15 is 30, 30 minus 26 is 4. So what's the 4th letter of the alphabet? D. So A gets sent to B, but N gets encrypted to B as well. B gets encrypted to D, but O gets encrypted to D. In fact, the same pattern goes through BDF all the way down to XZ, BDF all the way down to XZ. It's no accident that this happens. That sort of pattern is built into it, but it does mean that as far as a multiplier in ciphering, it isn't very good. Because if I have LRN and I want to decrypt it, knowing that this is the cipher, L could have been F, or it could have been S. So this could have been F or S. R could have been I or V. N could have been G or T. So we could have had FIG, or you could have had FIT as another possibility, or you could have had SIT. I mean, you could have even had FVT, or you could have had SVT, or you could have had SVG as the plain text. So the problem with this is there are lots of different plain text words, only some of them are English, but there are lots of plain text possibilities that get encrypted to the same ciphertext, and using a multiply by 2. And that is a real problem because the receiver really doesn't know which one was actually meant. So for that reason, we say that this is an invalid multiplier because this doubles up, or you've got repetitions. So then the question is, well, if 2 is good, but 3 is bad, if 2 is valid and 3 is invalid, sorry, if 3 is valid and 2 is invalid, so valid, invalid. If 3 is a good multiplier but 2 isn't, is there a pattern to this? Is there a way of figuring it out? Well, it turns out that it's a little bit tedious, but you can do this. The valid multipliers are basically everything from 1 to 26. Okay, 1 doesn't do much. It just, if you multiply by 1, you'll get the same ciphertext out as you put in as a plain text. 3 is okay. 5 is okay. 7, 9, 11, 15, 17, 19, 21, 22, 25 are all good. All the other ones, 2, 4, 6, 8, 10, 12, 13, 14, 16, 18, 20, 22, 24, 26, are bad. And you ask yourself, well, is there a pattern there? The answer is yes, there is a pattern. Okay. What's some patterns? I mean, your first thought might be, oh, even numbers. They're all even. They're all even. Oh, well, hang on a sec. 13 is not even. Okay. So it isn't just the even numbers which are multiplied. There's some odd numbers that are invalid as well. You might think, oh, 1, 3, 5, 7, 9, 11, prime numbers. Well, unfortunately, 15 is not prime. 21 is not prime. 25 is not prime. So it's not just the prime numbers, but some extra ones. So there are 12 valid ones, including a multiplier of 1, which isn't very sensible. And there are 14 invalid ones. We can stop at 26. We don't have to go to 27 because multiplying by, for example, multiplying by 33. 33 in the MAT1MIT system is equivalent to 7. So multiplying by 33 is actually the same as multiplying by 7. So we can actually stop there. These are basically valid and invalid. We don't have to go any further. But it still doesn't answer the question, why these don't work, but these do? And the answer, I was going to tell you what the answer was. Okay. Very briefly what the answer is. Remember that we're talking with the 26 system. The 26 system. Now, if you look at these numbers, so let's look at the invalid ones and compare them with 26. 2 and 26, you see that there's a common factor of 2. 4 with 26. Okay, 4 doesn't go into 26. Okay, 26 is not a multiple of 4, but there is a common factor. So 2 goes into 4 and 2 goes into 26. 6 doesn't go into 26, but there's a common factor. Okay, 8 doesn't go into 26, but there is a common factor. Okay, same with 10. 10 has a common factor with 26, namely 2. Same with 12. 12 has a common factor with 26. 13. Okay, it isn't even, but it has a common factor with 26. So 13 goes into 13 and 13 goes into 26. Okay, now we go back to 14, 16, 18. All of these have a common factor with 26 that isn't 1. These ones, 1, 3, 5, 7, have no common factors with 26. So there's no number that goes into 25 and into 26. There's no number that goes into 15 and 26. So remember, we talked about these being technically co-prime. So they're not just the prime numbers, but there are extra ones like 15, which are co-prime to 26. There's no common factor. So what are the factors of 15? 1, 3, 5, and 15. What are the factors of 26? Apart from 1, well, 2 and 13 and 26. So no factors of that common to that. Now you see why we started to, one of the reasons why we started to look at common factors earlier in the semester. Just move for a minute. Yeah. Now there's a mathematical reason for why that's true, but it's a really neat pattern. Right. So I've answered the question ahead of time. What's valid and what isn't. But let's just go through another little example. So we've got plain text cry. We're going to use a multiplier of 11. 11's okay. It's on a list of valid things. It doesn't have a common factor with 26. So actually, I'm going to set it out this way. So here's our encryption technique. Take the plain text number, multiply by 11, reduce mod 26, and that's the ciphertext number. And then you encode it back into letters. So I'm going to write it this way. C space. So that's plain text. Now, it turns out that C is the third letter, R is the 18th, and Y, I think, is the 25th. Multiply by 11. So we've got 33. 11 times 18 is 198. 25 times 11 is times 11 is 275. Now we've got to reduce mod 26. So I'm setting this out in a template because something very similar is going to happen in a little while. Okay, reduce mod 36. So you can just subtract 26, and that would leave you with 7. So 33 and 7 are the same in this mod 26 arithmetic. 198. Okay, what are you going to do with 198? Well, just over here on your scratch pad, 198 is 7 lots of 26, and the remainder will be 16. So 7 26s go into 198, and with 16 left over. So that gives us our mod number. And scratch pad over here. How many 26s go into there? Probably 10. Okay, so that will give you 216 with 15 left over. Okay, what's the 7th letter of the alphabet? G. What's the 16th letter of the alphabet? P. What's the 15th letter of the alphabet? The one before it? O. So this is our ciphertext. So cry gets encrypted into GPO. And notice that I'm keeping this convention of lowercase for plain, uppercase for cipher. That just helps us to keep a track of things. Now you'll notice that I've set it out slightly differently to this. This just does it one letter at a time. Okay, so third letter, 3 times 11 is 33, reduced to 7, and then 7 is the corresponds to G, and so on. But this tabular form is really good for when we get a more complicated encryption process, and also when we want to decipher or decrypt, because decryption is going to be also quite important for us. So, decryption, that's the other half. It's no use sending a secret message if the other person can't decrypt it. So when we did the additive one, okay, with 3, the decryption, we could either subtract 3 or, what was the same thing, adding 23. Remember the clock face? 1, 2, 3, all the way down to around to 25, 26. So if I start at 25 and I add 3 to encrypt, I get to 2. That's the encryption process. But if I want to decrypt, I have to move backwards, subtract 3. So -1, -2, -3, and I get to 25. Or I could add 23 and go around this way. So 23 plus 2 is 25. So the decryption is either subtract 3 or add 23. They're the same, and that's because -3 is the same as 23 in the mod 26 system. So adding 3, how do I decrypt? I do the opposite, subtract 3. Now, with a multiplicative cipher, we're multiplying by 3. So we want to multiply by 3. So how would you decrypt? Well, what's the opposite of multiplying? Well, it turns out that that in ordinary arithmetic, you say, oh, if I want to undo or multiply by 3, let's just divide by 3. Okay, so unfortunately, it doesn't quite work. Think about it this way. Suppose you've got the fifth letter, which is E, as your encryption. And you divide by 3 to get the plain text letter. So you're going to attempt to decrypt by dividing. So what's the 5/3 letter of the alphabet? Well, it doesn't make sense because there isn't a 5/3 letter. The letters, it's either the first letter or second or third or fourth or fifth. And 5/3 is somewhere between the first and second letter. So there's no letter in between the first and second letter. So decrypting by dividing by doesn't work. So what we're going to do is something really tricky. This is partly why I talked about this. So with the additive cipher, we add 3 to N cipher, and to decipher, we subtract 3. But we turn subtract 3 into an add. So to encrypt, we add 3. To decrypt, we subtract 3, but that's the same thing as adding 3. So what we're going to do is, instead of when we encrypt by multiplying by 3, the decrypt is going to be done by something similar. We're going to be multiplying by something. So encrypt for an additive cipher, decrypt by adding a correct amount. Encrypt with a multiplicative cipher, we're going to decrypt by multiplying by a certain amount. And the trick is, what is that amount? This is what's happening here. We're going to use a multiplication process to do the decryption. Okay. I'm going to do this one just slightly differently. I'm going to ask you this. Okay, just for the additive, additive cipher with shift +3. Okay, when we say -3, what does that mean? Well, it's the thing that you add to 3 to give you 0. Okay, but remember, we're working in the MAT1MIT system. So I remember talking about this way back in about the first week of semester. We define -3 to be the thing that you add to 3 to give you 0. And we can do the same thing in the MAT1MIT system. So if I ask you, in the MAT1MIT system, what do I have to add to 3 to give you 0? So here's 1, 2, 3, 26, 25. So I start with 3. What do I have to add to give 0? So remember, 26 and 0 are the same. Well, I've got to add 23 to get around to 0. So 23 is actually the same as -3. So -3 is the thing you add to 3 to get to 0. 23 is the thing you add to 3 to get to 0. Because remember, 0 and 26 are the same. So with the multiplicative cipher, okay, we multiply by 3. Okay. How do you undo divide by 3? How do you undo multiply by 3? Well, ordinarily we say divide by. What we want to do is okay, I was going to say this. Okay. In ordinary arithmetic, if I say 15 divided by 3, okay, what's really happening is we're saying 15 times 1 over 3. And what's 1 over 3? 1 over 3 is the thing that you multiplied by 3 to give you 1. Okay, so dividing by 3 in ordinary arithmetic is the same as multiplying by the reciprocal of 3. What's a reciprocal of 3? It's the thing that you multiply by 3 to give you 1. So 15 divided by 5 is the same thing as 15 times 1 over 5. Okay. What's 1 over 5? 1 over 5 is the thing that I have to multiply by 5 to give me 1. That's kind of how we define what 1 over 5 means. So here we're going to be doing this in the MAT1MIT system. Okay. I'm asking myself, I want to encrypt by multiply by 3, decrypt by sort of doing something that's equivalent to dividing by 3. And notice what I've done here with ordinary arithmetic. Dividing by 3 in ordinary arithmetic is multiplying by something else. Dividing by 5 is multiplying by something else. 3 halves divided by 5 quarters is the same thing as, remember our rules for fractions, 3 halves multiplied by the reciprocal. So dividing by something is equivalent to multiplying by something else. Encryption is multiplied by 3. Decryption is divide by 3. So how can we turn the divide by 3 into a multiply by something? The idea is we ask ourselves, we're going to multiply by something in the MAT1MIT system. Okay. What times 3 gives us 1 in the MAT1MIT system? Okay, well, 1 times 3 is 3, so that doesn't work. 2 times 3 is 6, that doesn't work. 3 times 3 is 9, that doesn't work. 4 times 3 is 12, that's not equal to 1. 5 times 3 is 15, that doesn't work. 6 times 3 is 18, that doesn't work, it's not equal to 1. Let's go a bit further. 7 times 3 is 21, nope, that doesn't work. 8 times 3 is 24, nope, that's not equal to 1. 9 times 3 is 27. Okay, that's bigger than 26, so we have to reduce it. Subtract 26, that's equal to 1. Ah, that's interesting. 9 times 3 is 1 in the 26 system. So 9 is kind of like 1/3. Okay, I mean, it isn't equal to 1/3, but it sort of acts like a 1/3. I mean, the definition of 1/3 is that which you multiply by 3 to give you 1 in the ordinary arithmetic. 9 is that which you multiply by 3 to give you 1 in the 26 arithmetic. So what we say is that 9 is the multiplicative inverse of 3 in the mod 26 arithmetic. That simply means that 9 times 3 is actually equal to 1 in this arithmetic. And how we denote that is we say, instead of writing 1/3, instead of writing 1/3, we're not going to write that. What we're going to write is the inverse of 3. So we write this out. And just be careful, that doesn't mean 1/3 like we've been doing with ordinary arithmetic. What we say is that this is the multiplicative inverse of 3. Or just the inverse of 3 is equal to 9. So this is really quite interesting about how this mod 26 system works, that you've got two things which multiply together to give you 1, and that's not a fraction. And that's not a fraction. So for our decryption, where we wanted to decrypt by dividing by 3, what we're actually going to do is to decrypt by multiplying by 9, because multiplying by 9 is the inverse of 3. So the encryption is the ciphertext is 3 times the plain text number, mod 26. The decryption is the plain text is 9 times the ciphertext number, mod 26. And the connection between the 3 and the 9 is this. So let's just make sure that works. I'm just looking for my notes from before. Can't find it. Something's gone missing. Okay, let's just go back to this. ABK gets turned into CFG. So ABK. Okay, so we're going to use multiplicative cipher with multiplier 3. So A is 1, B is 2, K is 11. We multiply by 3, we get 3, 6, 33. Reduce mod 26 gives us 3, 6, 7, and that gets turned into C, F, G. Now, let's just make sure that that works when we decrypt it. So, multiply by 3 to encrypt, we get CFG. Now, suppose we're going to, you're the person at the other end, CFG. You get CFG. So this is encrypt. This is decrypt. How are we going to decrypt? We're going to multiply by 9. So CFG are letters 3, 6, and 7. Multiply by 9 to decrypt. So 3 9s are 27. 6 9s are 54. 7 9s are 63. Reduce mod 26. 27 minus 1. 27 minus 26 is 1. 54 minus 26. Okay, so just do this down here. 54 is 2 times 26, which is 52, plus 2. So reducing 54, we get back to 2. 63 is 2 times 26 is 52, plus 11. So that reduces back to 11. What's the first letter of the alphabet? A. What's the second letter of the alphabet? B. What's the 11th letter of the alphabet? K. So, encrypted ABK by multiplying by 3, reducing to CFG. Decrypt by multiplying by 9, CFG 367 becomes ABK. 27, 54, 63 by 9. And then reducing gives ABK. And thankfully, ABK is what was originally sent. How are 3 and 9 related? 9 is the multiplicative inverse of 3. 9 is the multiplicative inverse of 3. Okay. So to decipher a multiplicative cipher with multiplier 3, we use a multiplicative cipher with multiplier 9. So APNOBEO, okay, you know that it was encrypted using this multiplier of 3. How do we do this? Write down the ciphertext, convert to their number equivalents, multiply by 9. Okay, we go through all that. Reduce each one of these mod 26. Okay, so the hardest one's going to be 144. So there's a bit of work involved, but you get these numbers reduced mod 26, and then the 9th letter is I, the 14th letter is N, etc. And the plain text was the word inverse. Now this slide is really just doing what I did before. It's saying 3 times 9 in the mod 26 system is 1, which is the same as 27. So 3 9s are actually 27, but in the mod 26 system, that is 1. So we have 2 numbers multiplied by each other to give us 1. So multiplying by 9 is kind of like multiplying by 1/3 in ordinary arithmetic. So we write instead of 1/3, so we don't use this notation, we use this notation. So the multiplicative inverse of 3 is 9. Why? Because 3 times 9 is congruent to 1. Now you ask yourself, well, what are the multiplicative inverses of all the other numbers? Okay, so what about multiplicative of 5? Multiplicative inverse of 5. So we need to find some number between 1 and 26 for which 5 times that is 1. And you could use trial and error. Okay. 5 ones are 5, that doesn't work. 5 twos are 10, no, 10 is not equal to 1, not congruent to 1. 5 threes are 15, that doesn't work. 5 fours are 20, that doesn't work. 5 fives are 25, that doesn't work. 5 sevens are 35, 5 sixes are 30, 30 is the same as 4, that doesn't work. 5 sevens are 35, that's congruent to 9, that doesn't work. So you work your way all the way through, and there's lots of dots in there. Finally, you get to 5 times 21. There's 105, and 105 is 4 times 26, which is 104, plus 1. So 105 reduces to 1 in the mod 26 system. That means the multiplicative inverse of 5 is 21. 5 times 21 is congruent to 1. The inverse of 5 is 21. That also means, this is important, if the inverse of 5 is 21, that must mean the inverse of 21 is 5. If the inverse of 3 is 9, that must mean the inverse of 9 is 3, because we've just got the same thing. What do I have to multiply by 9? So suppose I didn't know that. 9 times what gives me 1 in the 26 system? 9 times 3. What times 3 gives me 1 in the 26 system? 9 does. Inverse of 3 is 9. Inverse of 9 is 3. Inverse of 21 is 5. Inverse of 5 is 21. So we've got 2 for the price of 1. And just to finish up here, going back to these guys, what's valid and invalid? These numbers have inverses, these numbers don't. So 5 and 21 are inverses of each other. 3 and 9 are inverses of each other. Okay. Next time around, we'll see what are the other inverses of these others. These, there's nothing which you can multiply by 12 to give you 1. There's nothing you can multiply by 2 to give you 1. So these numbers don't have inverses. These numbers do. All right. That's a fair bit today. As I said, this is probably the most interesting, next to the most interesting part of the subject after we've gotten through all the, well, I was going to say tedious, but the sort of the algebraic manipulations, the manipulations with fractions, and so on. Now we're starting to get some really nice mathematics. And the thing with cryptography is that these methods are fairly easy to crack just by trial and error, but the general principles work for all sorts of encryption techniques. So what we're going to do next time, I think, is put the multiplication and the addition together. And so we're going to multiply and shift in one operation to make a more sophisticated code. It's still easy to crack, but just gives you a flavor of what's going on. Okay, that's enough for now. I'll see you when we see each other again on Thursday. Is that right? Yep, Thursday. Using the same Zoom link. Okay, so sorry, I've got a dash. I've got another class now. And if you've got any questions, don't forget to email me through the week. So I'll see you on Thursday.
Thank you.
Yep, thanks.